Hi, I'm George from the University of Southern Queensland, and I want to talk to you about the planets that we're finding with the TESS mission around young stars, and how they can help us place into context the thousands of other planets that we're finding around other stars. If we were to take a look at these thousands of planets and visualize them as if they were all orbiting the same star, this is what it would look like. You have the classical hot Jupiters, Jovian-sized planets that orbit within a couple of days of their host stars. Then you have the super-Earths and Neptunes, planets from 1 to 4 Earth radii that seem to be extremely abundant around Sun-like stars. How did these planets form? How did they evolve, and how did they get to where they are right now? We have a toy model of how we think these planets form. All planets form in their protoplanetic disks that are made of gas and dust. Over time, those gas and dust particles move around and they coagulate into protoplanet cores, that some of which get large enough to accrete the gas around it and become envelopes or atmospheres. As the disk dissipates over time, these planets become exposed to the intense stellar radiation that are left behind. And some of these planets and their atmospheres become evaporated away, leaving behind cores. There are a couple of outcomes of the model that we're presenting here. One is that if we were to observe these planets at an early age, they should all be very well aligned with the protoplanet disk that they were formed from. The other is that we should be observing mass loss through evaporation or through core heating over time. And so the planets that we're observing should have different densities to the planets that we're finding around mature age stars, and that we should be seeing escaping atmospheres for some of these young planets. Today, we know of dozens of planets around young stars, and these are the planet systems that we want to characterize in depth to better understand the mechanisms and the phenomena that we just talked about. This is a distribution of the planets that we know today around young stars as a function of their age on the x-axis and the magnitude of their host star on the y-axis. You can see that the planets we're finding today around young stars are a diverse group. We're finding some ultra-short period planets. We're also finding planets lying in multi-planet systems, much like those that we're finding around mature age stars that we're so familiar with. The contribution of the TESS mission are these. TESS is predominantly finding planets of a variety of ages, but around bright stars, stars that are suitable for in-depth characterization studies later on. That's the key legacy of what TESS is contributing to this field. Each one of these planets and star systems can be characterized in depth after discovery. The discovery themselves is more difficult than those of planets around mature age stars, and that's because these stars are rapidly rotating. They are young, they are spotty, and as we spin up these spots, you get photometric modulation in the light curves that we obtain with TESS. And we have to dig through that photometric modulation, these activity signatures, to find the transit signatures that are buried underneath. Nevertheless, we've been successful in detecting a series of planets that are young around noisy stars from TESS. And here are a couple of examples. HIP 67522 is an example of a hot Jupiter-like planet that is found around a star that's part of the SCO-SEN association at around 10 to 20 million years old. You can see that this is a great example of a noisy light curve going up and down, showing the spot-modulated rotational signature that's so common with young stars. Buried underneath are these transit signatures that reveal the transiting planet, a one Jupiter radius planet with an orbital period of about 7 days. Here's another example. AU-MIC, a star that is already known to host a debris disk, turned out to also host a transiting planet in a very short period orbit. This star may in fact actually host a couple of transiting planets and has an age of about 20 million years or so. Here we see not just the stellar modulation coming from the rotating star spots, but also stellar flares that are so common around low mass stars and stars that are young. DS-TUC was the first young planet that was discovered by the TESS mission. It's a Neptune-sized planet orbiting an 8-day period orbit around a star that's in the TUC orbit association at around 40 to 50 million years of age. The star is part of a visual binary system, and the team had to go and obtain Spitzer observations that followed up the transits to identify exactly which one of the visual binary the planet orbited around. These types of follow-up observations are so critical to enabling further in-depth characterization studies that we're going to talk about later on in this talk. Young planets are kept being discovered every now and then from the TESS mission, and I just want to advertise the work of Sidney Vack at Harvard, an undergraduate at Harvard, who presents a set of planets, a multi-planet system around a star that's about 500 million years old. One of these planets lie in the habitable zone of that star. It's very exciting. Go to see Sidney for her work. With the discoveries that we've had so far around young stars, we can then go back and examine the outcomes that we predicted earlier. Do the planets that we're finding right now around young stars lie in the same plane as the disk from which they were formed? If we were to make that characterization for planets that are small, around old, giga-year-old stars, we find that no, they do not. These planets that we're finding have a variety of different orbital inclination angles. Some have polar orbits, while some are well aligned. And that's an indication of what happened after they were formed. The planets form within the first 5 to 10 million years when the gas disk is still there. After the disk dissipates, the planets can interact with each other gravitationally, and some planets can get thrown inward dynamically via these types of interactions with nearby planets, with companion stars, or with passing by stars. And as a result, they can get migrated to their current orbits through dynamical means, and their orbit inclinations can get excited to what we see today. But what is the timescale of these mechanisms? Are they the dominant mechanisms for some of these planet populations that we're seeing right now? That's a timescale problem, and one that we can solve by looking for planets and characterizing the properties of planets around young stars. So if we were to make the same observation for young planets, this is what we see. Today we have something like 6 or 7 planets around young stars for which we know their orbital obliquities. And we see that they are all very well aligned to their primordial disks. How to make these observations? Most of which are from the classical Rossiter-McLaughlin observations. That is, you throw a transiting planet around a rapidly rotating star. Remember, these young stars are all rapidly rotating. And that planet is going to be first transiting across the blue shifted part of the star that's coming and rotating towards you, and then occulting the red shifted part of the star. As a result, you're going to see a net redshift and a net blue shift coming from that planet transit when you're observing the net radial velocity of the star in spectroscopy. Something like 160 systems have received these types of observations to date. Only a handful are young. A good example is DS-TUC, our 45 million year old system that we talked about earlier. Montet et al. And Bonetti et al. Made this type of observation using the Magellan Planet Finder spectrograph and with VLT espresso, and they came to the same conclusion that the system is very well aligned. The same can be said for AU Micbe, a planet around a debris disk hosting star at around an age of about 20 or so million years. And again, they found that this planet was in a very well-aligned orbit with respect to the spin of the star and presumably with respect to the primordial disk from which it was formed. But these observations are not trivial, not as trivial as they are for mature age stars, planet systems. And that's because these stars are extremely spotty. And so instead of a textbook Rossiter-McLaughlin signal, you have a star that's rotating with a set of spots lying on its surface. And the planet may occult some of these spots. The stars, because they're rotating, the star spot modulation signal causes this net change, overall large-scale variation in the photometry that we're seeing, as well as the spectroscopy, as well as the radial velocity that we're observing. We can fit these large-scale variations out with a polynomial, but you're still arriving with a Raster-McLaughlin signal that is affected by spots. Let's say there's a spot crossing event that's happening for this particular system. Then that spot crossing event can deviate from your textbook Raster-McLaughlin model. And when you don't know about the spot crossing event, and when you have noisy data, that can be misinterpreted as an asymmetric transit, leading to an assumption that the planet, leading to an inference that the planet lies in a misaligned orbit. Even if spot crossing events do not occur, just because these stars are spot dominated, you may have different parts of the stellar hemisphere being differently illuminated because of the spot composition. And so you may have asymmetric Raster-McLaughlin signals just purely from the asymmetry in the illumination of these stars. These types of error sources need to be taken into account when we're calculating the obliquity angle from a Raster-McLaughlin observation of a spotty star. There's one way around this, and that is to model the planet and the spots at the same time. And we can do this by examining the spectroscopic line profiles. This is very similar to the effect that we're talking about for Raster-McLaughlin observations. The planet is still transiting across a rapidly rotating star, still blocking out the blue-shifted and red-shifted part of the star sequentially. But instead of measuring the net red and blue shift of that star, we're mapping out the line profile, the spectroscopic line profile, and observing and looking for that dimple, that shadow that's cast by the planet directly. We can map that shadow as a function of time on the y-axis and the velocity of the shadow on the x-axis, and the direction of that shadow tells us what the obliquity angle of that planet is. It's not that simple again when you have spots. Here's a good example from our observation of DS Tuck in 2020. We found that in addition to seeing this planet transit signal, we're also seeing these shadows cast by the spots around that occupy this very young star. But you can, from the line profile, model both the shadow of the planet and the spot simultaneously. And when you subtract away the spot signal, you get back this crisp line profile variation caused by the transiting planet. And this type of detections are unambiguous. And when we do the spot modeling, they can reveal exactly what the spin orbit angle of the planet is. These types of spectroscopic follow-up observations of transiting planets have been performed for about half a dozen planets to date around young stars, and we found that they are all lying in very well-aligned orbits. I won't dig too deep into this, but this is a diagram showing what the distribution of these planets are in terms of their obliquity angle and in terms of their age. 0 degrees means that these planets are well aligned, 90 degrees are for polar orbits, and 180 degrees for misaligned planets. And as you can see, there are no misaligned planets around stars that are younger than about 100 or so million years old. I'll leave it to our speakers in the upcoming sessions, Alexei Heitzman, a graduate student at the University of Southern Queensland, and Chris Worth, an undergraduate student at Harvard University, tell you more about more recent observations for a set of young planet systems that we've been following up. The other outcome of our model is that of mass loss. We should be expecting these planets to undergo mass loss within the first couple of 100 million years of their existence. And so their composition at a young age, their densities, their radii should look different to that of the mature age planet population. We can show that distribution as a function of their orbital period and as a function of the planet radius. You may be familiar with these types of plots for planets around more mature age stars. We expect that these plots may look different if we were to show them for young planets. And that's because these planets over time undergo contraction, evaporation, and some of the envelopes for some of these planets can get blown away, evaporated away, leaving behind the rocky cores. There are a couple of mechanisms that dominate these type of interactions. One is photoevaporation. If the planet is lying very close to the star, it gets heated in the outer atmosphere gets heated and gets evaporated away. That heating comes from X-ray for stars that are around 100 million years old or younger for sun-like stars, and from extreme UV radiation for stars that are slightly older. And that's a dominant driver for atmospheric evaporation for planets that lie very close to their stars. For planets that are further out, they still have the residual heat from contraction. And so that heat can still heat up the upper atmospheres of these planets and cause evaporation that way. And so for planets that are orbiting further out, you may have evaporation still from core heating. These mechanisms are what drives this classical diagram, this period radius valley that we know so well from the Kepler planet distribution. Planets that are about 2 or so Earth radii or larger have some kind of an envelope, some kind of an atmosphere, whilst planets that lie lower on this diagram are mostly rocky cores, perhaps residuals of the process of evaporation. So where do the young planets that we're discovering lie on this diagram? Here are all the young planets that we've discovered with TESS to date, and as you can see, they're all relatively inflated with respect to the planets that we know that we know to be dominant around sun-like stars. Most of this is probably because of the detection biases that are present in our observations. Young planets are difficult to observe, to detect, because they orbit active stars. But you can characterize that detection bias by doing signal injection and recovery analyses like this type of analyses. Not many of these have been characterized properly for test systems, but Aaron's result made these type of analyses for Kepler and K2 planets that were discovered around young stars, and he came to the conclusion that actually, even when you take these biases into account, young planets are still more inflated than mature age planets. Here's the actual model predictions for how that evaporation process goes on. The rate of evaporation and the eventual outcome of evaporation is a function of how close you are to the star, what type of planet you are. That evaporation process happens over the course of tens to hundreds of millions of years, and is something that we can actually detect by looking for planets in those time ranges. Planets that have more massive cores end up keeping most of their envelope, whilst planets that have less massive cores tend to lose their envelope. It's a runaway process. I'm showing this because this is one of the best predictions in the exoplanet field. The presence of an occurrence valley, a valley in the period radius distribution, is one that was predicted before it was described from the Kepler observation, from the Kepler distribution. Here's a great paper from Owen Jackson that showed what types of factors influence the eventual outcome and the rate of evaporation. Within the first 100 million years, the planets are bombarded by X-ray radiation. Afterwards, UV radiation dominates. The rate of evaporation and the outcome of evaporation is a function of whether the planet is of higher mass, has a more massive core, or whether it's a Neptune-sized planet with a smaller core. The density of that planet really drives the rate of evaporation. The less dense that planet is, the faster the evaporation occurs. And so if we were able to map out a range of planets at a range of orbital periods around a set of stars that have different ages, we can actually take a look at how this process occurs in situ at these timescales. The mass radius diagram is one of the most important diagrams in exoplanets. It tells you the composition of planets as a function of their mass. But to populate this diagram for young stars, it's very difficult because of the stellar activity signal that we were talking about earlier. These young stars often have stellar activity jitter that are an order of magnitude or more larger than that induced by the planet's orbital motion about the host star. Nevertheless, there has been successes. K200 is probably the best example. It's a planet in a very short period orbit around a star in the Hyades in the Precipice cluster around 600 to 800 million years of age. And the group was able to obtain about 80 observations with HARPS North, disentangling the stellar activity jitter and that of the planet to reveal a Neptune mass planet that lies underneath. We hope that as more and more spectrographs come online, especially those in the infrared and in the red optical end, we should be able to disentangle the stellar activity signal from that of the orbiting planets and reveal the masses of more of these planets. And we hope that maybe they might show us what the densities of these young planets may be. Perhaps they are less dense than those that we're finding around mature age stars. Right now, though, one of the best measurements that we can make is that of the ongoing evaporation process by looking at signatures of atmospheric escape. This means taking a look at the transit signature coming from the planet in Lyman alpha, H alpha, helium, and a bunch of other evaporation signatures. The idea is that it's fairly easy to detect these signatures if they are present, indicating that these lighter gases like hydrogen and helium are escaping away from the atmosphere, inducing transits that are many times the size of the transits of the photosphere of the planet itself. Here's an example of the observation for HD 209458, the very first transiting hot Jupiter. This was the first example of atmospheric escape from any planet, from any exoplanet. The Lyman alpha line is a UV line at around 1,200 angstroms. Here's the line from the star, and it's subdued by an interstellar absorption line. The interstellar absorption line comes from the material from between us and the star itself, and is itself invariant. But the depth of the line around it, the line coming from the star, between the difference in depth between in transit and out of transit tells you what the size of the planet is in Lyman alpha. When this observation was first performed with HST, with the TESS instrument for HD 209458, they found that the planet had induced a transit of about 10% in depth, as opposed to about a 1% transit for this planet in optical, indicating that the planet has an extremely large hydrogen envelope enveloping it. Lyman alpha escape was subsequently actually observed this year for HD 63433, a Neptune-sized planet lying in a planet system in Ursa Major, the moving group Ursa Major, with an age of about 400 or so million years of age. In this case, the planet is Neptune-sized. Its transit is a lot shallower than 1%, but the Lyman alpha transit of the planet is almost 10% in depth, indicating that yes, it too has an escaping hydrogen envelope. We hope that we can make these types of measurements for more planets with HST and with ground-based facilities in H alpha if it's there, and also in helium. And that might tell us something about the mass loss rate for these planets as a function of age and the type of planet that we're observing. And so we can summarize by going back to the predictions that we had stated earlier. We should expect that the planets around young stars should all be very well aligned. And that is so far to be true for the 7 or so planets that we've measured to date. This juxtaposes the same measurements performed for similar planets around mature H stars. And it raises the question, when does misalignment happen? And are there multiple populations and multiple pathways for the formation of closely Neptune-sized planets? Mass loss. We should be able to measure the occurrence rate of planets as a function of age, period, radius, fairly easily from our TESS observations. Compare that to the same types of planets around mature H stars. Should we see more inflated planets around young stars? As we get better with measuring and disentangling radial velocity jitter from the radial velocity orbit of the planet, we should be able to measure the mass radius age relationship and see that evolve over time. And finally, there are signatures of ongoing evaporation detected for some of these young planets. And we should be able to compare the mass loss rate calculated from these signatures with that expected for those environments and check our models. All these have been enabled by the planet discoveries that we've made so far for planets around young stars. The TESS contribution, the TESS legacy for this aspect should be that of the discovery of dozens of young planets across the whole sky of a variety of ages around bright stars that are suitable for characterization studies like those that we talked about today. Thanks very much.